Let's learn about neural networks. So neural network is nothing but a network of neurons. So this is loosely inspired by neurons in human brain. So mathematically, so neural network is nothing but a system of functions that learns from data. So here we have three main layers or components in neural network. First one is the input, hidden, and output layer. So the input is where we give the models feed in the input data. So let's say if we want to predict the price of a house, we have input features like number of bedrooms or the area of the house and so on. And each of the circles, which is called as neurons, constitute the neural network. So if you see a single neuron, what it does is it takes an input, does the computation, and gives the output. That's it. So it might sound simple, but when they are arranged in a network fashion, this network of neurons can help to learn complex functions, which is useful for the model's prediction. So most importantly, this neuron, they doesn't only compute, they also learn by adjusting few internal parameters, which we're gonna see. So by adjusting these parameters, the network's prediction, which is become more accurate over time. So let's talk about the learnable parameters of neurons, which is the weights and bias. The weights control how strongly one neuron influences other. So neural networks features are not engineered like in the traditional machine learning model. Instead, the network learns the internal representation of these features by adjusting these weights automatically. It doesn't learn the feature directly, but it learns the internal representation. For example, by classifying an image of a cat, let's say a cat or a dog. Pardon me for the drawing, but so here the hidden layers, which is gonna actually learn the patterns. They can learn the representation of these features, like which correlates with things like the edges or texture of this image of the cat, or like the whiskers, which cats have, and things like that, so that the neural network can predict efficiently. So next one is the bias. So bias is an offset term that shifts the neuron's output. We have a single neuron and shift this neuron output. So it allows the neuron to activate even when all inputs are zero. So what does that mean? So neurons, let's see the neuron equation. So the neurons, Z is the neuron's output. We have W dot product of X plus V, where W represent the weight or the weight vectors which all the neurons have, and X is the input value which gets given here or which gets passed on here, and B is the bias, which is the offset which we define. So even if the weights are zero, this term would be zero and we will have the bias. So that's why I mean by it allows the neuron to activate even when all inputs are zero. So for example, if a house, let's say in the house price prediction, even if the house has zero bedrooms, it may still have a base price, right? Let's say, for example, $50,000. So this base price is what captured by this bias. Now let's see the intuition of activation function. So let's recall the equation for the neuron. So this is called as weighted sum, because for a particular neuron, this weights which is incoming to the neuron, this, let's say this neuron, this weight, this, when every weight is multiplied with the corresponding input, which is X, and added with bias. So if we see this is just a linear function, and if you see the dot product between the weights and input, which is nothing but it shows this similarity. So it tells how the weights are aligned in the direction of the input, so that if this dot product value is more, they are highly correlated, which is useful in predicting the outputs by the neural networks. So that's the significance of this. So, but what if here we want non-linearity? So here we have a linear function. So without this activation, the neuron would behave like a simple linear model like this. So stacking these layers would also result in a linear function. Why? Because if this neuron has this linear function and next neuron also has this linear function, and if we add them together, it will be still linear function. But we want the neural network to learn complex and curved decision boundaries. Complex and curved decision boundary, which is not possible with just these linear functions because it is only useful for representing straight lines. So for that case, we have to introduce this activation function. So after producing the weighted sum, its process-based activation function to improve it, introduce non-linearity so that it can learn more non-linear complex patterns. So activation functions can be anything. For example, we have ReLU, a linear unit, where if the output of a neuron is negative, it's zero, and if it's positive, it's the same value. And we have similarly other functions which we're gonna see later. So it can also constrain the outputs to useful ranges. It can also constrain the output into useful ranges. Why? Like if example the output is a probability between 0 and 1, we need to confine the output of the neuron, which can be ranging any number from like minus infinity to infinity or something. So this is not making any sense for the probability value between 0 and 1. So this activation function can help it to confine this within 0 and 1, so it can be well understood and represented by the model. Now let's talk about the overall flow of the neural network. So first, the step begins with the forward pass. Here we start with the input, and the inputs flow into the network with randomly assigned weights to the neurons. So why the weights are randomly assigned? Because of the weights in the neuron, if they are initialized the same, they would be behaving identical way. Why? Because the weight, its purpose is to learn the feature representations by this each neurons. But if they're initializing the same, they would learn the same feature representations, and it won't be nice. So that's why we initialize them differently to learn the different feature representations. So after passing that, we will get an output value. So this is the predicted value of the neural networks. So next we have the actual value. So we need to measure the loss, like how far is the actual value is different from the predicted value. So for that, we need a loss function. So this calculates the error and it measures how wrong the prediction is. So high loss means the prediction is far away from the actual value, and low loss means the prediction is actually close to the actual value. So now that we know, how far it is, the actual value is far from the predicted value, but we need to reduce this loss. Reduce this. So we need to know how each weight in the network contributed to the error in the final output. So, but we cannot directly know by seeing it. So that's where the concept of gradient comes in. So gradient is a technical term. It just intuitively it just tells the direction and magnitude in which a particular weight, like let's take this neuron. So particular weight should change. So whether weight in this neuron should like increase or decrease, or how much it should increase or decrease, so that the final loss, which is the gap between the actual and predicted value, this loss would be minimized. But it's just for single neuron, but we need to do it for every neurons, right? So that's where the process of backpropagation comes in. So using this gradient which we calculate from the output, we are going to propagate this error backward to the network again, so that each weight would learn the gradient and everything, and it will update the weights so that the loss is minimized and the weights are being efficient. So this process can be repeated so that the neural networks can completely learn the data and give efficient outputs. So let's quickly go through example of a forward pass with numerical example of a neural network. So here let's take this neural network structure. So here we have two input neurons, x1 and x2, and single hidden layer with two neurons each, h1 and h2, and output neuron O. So let's look at the notations here. So here we have the weights. X are the weights, and X is the input, and W is the weights, and V is the bias. And V is also the weight, but just because it's in the output side, I mentioned with V. So let's see how to properly represent this weight. So here, this term here is the proper notation of the weight. So W subscript ij, and then the superscript we have the L. So L is the layer number. So here we have, this is layer 1, the hidden layer. So if we take example of this weight, just going from x1 to the second neuron of the hidden layer. So here the layer in which the neuron is present, it is going to is represented by this L. So this weight in superscript we need to mention 1 because it's going to the first hidden layer, and the I represents to the neuron number in which it is going through in the layer L. So which neuron is it going through in the layer L? We have the neuron 1 and 2. The layer L is going to the second layer, so I must be 2. And which neuron is it coming from the previous layer, which is L minus 1. So in the previous layer, it's coming from first neuron. This is the second neuron in this layer. So first neuron is coming from 1 to second neuron of the first layer. So due to that, because it's coming from the first neuron, the J, we need to keep it 1. So that's why we get W subscript W21 of the first layer. I didn't mention the layer number because we have just single layer and it would be a little clutter if I mentioned through the calculation. So that's why I ignored it for the moment. So this is how to properly mention. So let's take another example. So here, let's take this one. It's going from second neuron of the input layer to the second neuron of the hidden layer. So what layer is first layer of the second neuron of the first layer? So if you want to mention this way, it's going through the second neuron. So second neuron means first is going to the first layer and is going to second neuron. So I must be 2. Where is it coming from? Which is the J. It's coming from second neuron of the previous layer, L minus 1. So 2. This is the representation which we assigned already. The numerical value is 1. So this is how we need to mention the weight. And here similarly, it's going to the next layer, which is the second layer. So the V2 actually would be like W layer is 2, and because it's coming from the second neuron of the previous layer, we just need to mention 2. Similarly here it will be like 2 and 1, but for simplicity I just mentioned as V1 and V2. Similarly, we have biases for the neurons. So for hidden layer, we have the B1 and B2 for each neuron. And output neuron, we have B0. So the activation functions which is used in this hidden layer is ReLU, which we'll see in a moment. And the output we use sigmoid. So first step, as we know the forward pass, we need to calculate with the inputs, we need to calculate the weighted sum, and we need to process it through the activations, and we need to propagate till the end till we get the output, and we need to find the loss by comparing with the actual output. So here the actual output target is, let's say, 1. So it's either 1 or 0. So this situation, yeah, it's like binary classification. The output is 1 or 0. So yeah, so let's move on to the general formula of calculating the weighted sum. So this is the formula of calculating the weighted sum. So here, for a particular layer, so the weighted sum is nothing but the summation of the dot product of the weights and the inputs in this case, or activations of the previous layer. If we have like more hidden layers, input won't be passed here because the output of the previous layer would be an activation value. So that's why we have a j here, a subscript j. So it's just multiplying the weights with the previous activation of the previous layer, then adding with the bias of the current layer. So let's see example quickly. So here, this first layer, let's say we want to calculate weighted sum of first neuron in the hidden layer, which is Z1. So what are the incoming connections here? So we see W11. So we need to multiply this with dot product this with the input here, with X1. So it's we have here. And what is the next connection? We have this one and this one. This is W12 multiplied by dot product of this X2. So we have this, then we calculate for H1, and we don't forget to add the bias term here. So similarly, for H2, we will have two connections incoming. So this would be this weight multiplied by this input, which is W21 X1, and we have W22 multiplied by X2, which is here, and added by this bias. So that's how we calculated the sum of these two neurons here. So we have the calculation here. We just substitute the values and we get the values for each. So after calculating the weighted sum for this, what is the next step? Next step is not the output. We have activation function which we need to calculate the value for. So there are many types of functions. Okay, we used ReLU. As you know, activation function is used to introduce non-linearity between the neural network layers, so that we can achieve non-linearity, or we can fit the data in non-linear patterns or curves, because the normal formula which we have is just the linear function. So if we have just two linear layers, the output also will be linear. So here it acts like a gate which allows only certain amount of information to pass through. So what do I mean by it? So ReLU, so this function would be looking like this. ReLU offset max of your offset. So the graph here, so whatever input which we give, the answer will be just the maximum of 0 or that value. So if we have an input, all the negative values would be 0, because the maximum is either 0 or that value. So all the negative values would be changed to 0, and if it's a positive value Z, it will be the same as Z itself. So if it's negative, it will be 0. If it's positive, it will be same as Z. So that's what ReLU does. It introduces non-linearity in this linear pattern. So if we apply that, here the ReLU of this Z1, so this we need to apply this to the weighted sum which we calculated before, which is -1. So -1 is negative, so it will be 0. If it is positive, as in the second case, activation would be 5, the same number as itself. Okay, so now we calculated the activation function results for these two neurons. So the next step is calculate the weighted sum of the output. So in the output, this is the formula to calculate the weighted sum, which is nothing but dot product of the weights and the input. Here it's not the input, it's the previous activation, which is A1 and A2 correspondingly. So we have V2 into V2 dot product of A2 and V1 dot product of A1 here, plus don't forget to add the pi. So if we just substitute the values, we will get minus 5 as here. So here, as we saw, our output here is either 0 or 1, which is a binary classification problem. So in that case, another activation function is applied, which is called as sigmoid. So this we saw already in the logistic regression video. It just scales the value from any number between the range of 0 and 1. So it's only in values of 0 and 1, so that we can actually measure how far the output is between the class 0 or class 1. So it is actually quantifiable in the current scenario of binary classification. That's what we do here. So we apply the sigmoid function for this output minus 5 which we got. So if this is the formula, so if we just calculate, this would be the answer, which is the predicted value, which is denoted by y cap. So this is the predicted value and these are the activations. So next step after we find the predicted value is to calculate the loss from the original, which is the target, and the predicted value. So here we use binary cross entropy loss. So what do I mean by it? So this loss is given by this formula. Does this seem familiar before? So this one is actually what we derived in logistic regression, but it had the only difference is it had average over m term, but here we just have the error term. So this is nothing but a negative log likelihood of Bernoulli, which we already derived in the logistic regression video, which you can see there. So this acts like switch. So if the output is actually the predicted output, the target output, if it is 1, so if we have 1 here, this term would be cancelled out and the output will be just this one. If you put 1 here, this will go, so it should be minus log y cap. So instead, if the output is 0, if we have 0 here, this will be the 0, this term will go out and we will have this term alone, log of 1 minus y cap and minus. So this is how it acts like a switch, but in our case we have target as 1, so that's why we get this formula for the loss, and we have the y cap value already. We can just substitute here. If we take the log value, this is what we get the value of the loss finally. So now that we completed our forward pass, we just took the input and we just processed it by calculating the weighted sum and the activations, and finally we got the output and we compared it with the target with the loss function BCE to get the loss. So now our goal is to backpropagate this loss back to the all neurons so that the weights can be adjusted such a way that the loss is minimized. So that's what we're gonna see next. So let's quickly talk about the idea behind backpropagation. So we have the loss function value, and our goal is to update each and every weight in the neural network, which is, let's take the WI. So we're gonna update it in such a way that this is the general form, we're gonna subtract the weight with a component. So this component where we can see this symbol, which is learning rate, which we're gonna see soon, multiplied by the partial derivative of the loss function with respect to the particular weight itself. So we're gonna subtract this in order to update the weight in each and every neuron. So why we need to take the partial derivative? As we can see, the partial derivative in the numerator, we have the loss function. On the denominator, we have the particular weights. So by taking the partial derivative, this value says that how the loss value gets changed if the weights, particular weights, gets nudged a bit. So if they get nudged a bit, how sensitive it is to the loss. So that's the significance, and that's why we take the partial derivative of each and every weight and biases. And we need to calculate this value so that we can update the weights. So if the value of this, the magnitude is very large, it says that this weight, particular weight, contributed to a lot of error or the loss functions. And if the value of the magnitude is very less, you can say that it's least significant. On the other hand, if it's like 0, the weight doesn't even matter in this situation, which that means it's not contributing to the loss function change at all if the weight is changed. So if it's 0, we can see that the weight has not changed its value because this term will go and we'll just update the weight to the same value. So why we need to take the partial derivative but not the full derivative? So again, so let's take this example. We need to update this particular weight, which is W22. So partial derivative ensures that the rest of the weights are free, because we want to ask the question like, what is the change in loss function only if this particular weight is being changed and other weights are kept same. So that's why we take the partial derivative here. So here we have the loss function. We can ask like, why not take directly the partial derivative of the loss function with respect to each and every weight? We cannot do that directly. So because we have a dependency chain, because the loss, as we calculated, the loss is dependent on the y cap value here, and y cap is dependent on these the weighted sum of the output, and it's dependent on the activation value, and similarly Z1 and Z2, and then only we have the weights. So we can clearly see there is a dependency chain. So that's why we need to calculate the partial derivatives or the gradients. So here comes the concept of gradient. So essentially the main goal is to find the partial derivative of each and every weights and biases, right? So we have partial derivative of this one, W11, 12, and similarly 13, 22, and the biases and so on. We need to calculate all of this. We cannot do it directly because of this dependency chain. So these all set of the vector, all set of the partial derivatives of the weights and biases is called as gradient, which is in form of a vector. So here theta is the parameters, the weights and biases. So all this we need to calculate in order to update each and every single weight. So this is called as gradient. So technically this whole vector is called gradient, but for explanation purposes I'm going to call each and every term gradient with respect to each and every parameter. So we saw the dependency chain here. So that's why we cannot directly find the partial derivative of loss function with respect to weight. We need to calculate these every things. So that's where chain rule comes, so that we can efficiently trace back the error, the loss function, to the previous way, so that we can update it efficiently. So this backpropagation is nothing but a repeated chain rule in order to get the updated weights. Okay, so let's work on the numericals from the logs function. So first step is here where I marked 1, 2, and 3. So first step, every connection is like, we can assume in a way that it's reverse. So we're gonna go from loss back to the weights. So the first step, what we have here is the BCE binary cross entropy loss back to the predicted value y cap. So here we have the BCE loss function. This is in case if the true label is 1, which we saw the equation before. If it's 0, we'll have another equation. So here we have the y cap value, and we're gonna first find the gradient with respect to the y cap, which is the predicted value of this loss function, because that's what we have here. So derivative of log x is 1 by x, so we have this here, and we're gonna substitute this value 0.0066 in order to get this gradient value. So this is from loss to the predicted value. So now we're gonna calculate back from the prediction to the output pre-activation part. So here we're gonna go from prediction to output pre-activation part. Here we have the sigmoid functions. So this is what we need to calculate. So we're gonna calculate the partial derivative of gradient of y cap, which is the prediction, to the pre-activation part. So we have set out as the pre-activation part, which is weighted sum of the output. So this, we get this formula y cap in 1 minus y cap. So let's see how we get that. So here the y cap, which is the predicted value, it's just a sigmoid function as we saw here. So it will be 1 by 1 plus e power minus z. So minus 1 is for the denominator part if this is present. So now we're gonna find the partial derivative of this with respect to z. So this is a function inside a function. So this outside function is x power n. So we will have this term here, and we're gonna add minus 1 here. And inside that we have another function. So e power minus z is the same value, same answer if we derivate it, but just because we have the minus, we have extra negative sign here. So this can be simplified. So this is the term what we have. So if we simplify this, we will get this term, and this term we're gonna do a substitution. We have y cap value. If we just keep the e power minus z on one side and take everything to the rest, we will get this one. E power minus z is 1 minus y cap by y cap. We're gonna substitute this again here. So what would it look like? We will have 1 minus y cap by y cap, and in the denominator we will have y 1 minus 1 by y cap, the whole square. So if we just simplify this again, we will have the same thing, this one, y cap into 1 minus y cap, which is what we got here. So this, we have the y cap value already. So what we're gonna do is we just gonna substitute this here and multiply in order to get this gradient value. So let me erase it quickly. Okay, so now we completed the first and second part. So we came from loss to predicted value, and we came to the output pre-activation. So from this output neuron, we calculated everything. So we need to assign a term in order to account for all the downstream effects from the neuron. Effects by effects I mean the partial derivatives, because there are two terms, right? So we introduce another term which is called as error signal, which is delta, which is delta of output, which we mentioned here to represent the error which is a downstream of all these things after the output neuron. So that is the prediction to pre-activation to the prediction and prediction to the loss. So how can we combine this? We can combine this with chain rule. That is, we just multiply the partial derivatives. So, so this is the step 3, which is the error signal. So we just do a chain rule in order to combine and multiply the partial derivatives of gradients. So here we can see the gradient of loss function with respect to the z, which is weighted sum of the output, is nothing but we can represent this in form of these two, which we calculate here. And these two we found the values already. We can just substitute and find the output for it. So if we see carefully, for cases where the neural network has binary cross entropy loss and sigmoid activation, this error signal can be simplified to just this form, y cap minus y, which is predicted minus the actual value. And so now let's see the fourth step. So what we got so far, we got the output signal, which is the delta out, which constitutes the effect from this part. So now we're gonna go more backwards. So here, so the next step is to compute the gradients of the output layer parameters. So output layer parameters means we have these two weights and a bias here. So we need to take the partial derivative or the gradient. So this is the weighted sum formula of the output neuron. So if we take partial derivative or gradient of this with respect to v1 and v2 and v dot, which is the two weights and bias. So if we just derivate this, we will get a1 cos this the only coefficient, and v2 this is the only coefficient, and this is this doesn't have any coefficient, so we will have 1. So now that we have these, we need to calculate the gradient of the loss function with respect to these. So how do we do that? So first we're going to find the gradient of the loss function with respect to this first v1 alone, which is this one. So this, if you recall the chain rule, we can represent this as the multiplication of the gradient, the loss function with respect to the z out and the gradient of z out and v1. So this one we already calculated here. So this we already calculated and carried from this. So recall, this is represented by the delta out, which is the error signal. So this is what this formula is. If we go to the previous part, so we can substitute this part with delta out. That's how we have the delta out, and this one is literally a1. So for this value we calculated previously, and a1 is nothing but activation, so which we calculated during the forward pass, so which is here. After the ReLU, we just calculated it to be 0 because it was a negative value. So that's why you can see the value is 0. So what does it say? It says that this is the dead neuron because it doesn't supply any useful information to the v1. So the next one is we have to calculate the gradient loss with respect to v2, which is the second weight. So similarly, we have the same formula, but instead of a2 we'll have a1, will have a2. We calculated it to be 5, so we have 5 here. So if we multiply these two, we will get 4 minus 4.96, right? 966 something. So yeah, that's how we get these two. So we calculated the gradient with respect to this weight, and we calculated gradient with respect to loss function with respect to this weight, and next one is the bias. So we have the bias. So using the chain rule, we will have this gradient of the same thing, but here instead of v1 we will have B naught, which is the bias of the output neuron. So this thing we already calculated this to be 1. So this will be substituted here. This whole thing will be 1. So it will be left it only with the delta out, which is the error signal output. So that's why we just mentioned here directly. Let me just clear the screen. So the delta out value we calculated already to be minus 0.993. So we have this one, we have the required terms, we have this one, this, and this. So for the output part, we calculated the gradient with respect to loss function of this, these two weights and bias. So next step is when we're gonna go back again. So now we're gonna pass the gradients back to the previous layer, which is the hidden pre-activation, which is through the ReLU gauge itself. So here after this we're gonna calculate the error signal from the hidden layer neuron 1, H1 and H2 respectively, these two. After this we calculate this, we can calculate the error which is passed down, which is the gradient which is passed back from the downstream components from this loss up to here. So here we will have the error signal of output, here it's 1 and here the error signal 2. So this is our main goal here. So let's go ahead and solve this. So first we have the activation formula, which is the ReLU of the weighted sum set I. So if we take the gradient of A of phi with respect to set of phi, we will have this ReLU derivative of ReLU of set of phi. So derivative of ReLU of set of phi. So ReLU function is ReLU function of z is z itself if it's positive and 0 if it's negative. We take the derivative. Z is 1, derivative of 0 is 0. So if it's the ReLU derivative of z function, if the z value is positive, it will be 1. If it's negative, it will be 0. So let's go ahead and solve the equations for the error signals. So for H1, the Z1 value which we calculated, which is the weighted sum, which is during the forward pass it was minus 1, which is less than 0. So the derivative of ReLU would be 0. So this value we're gonna use it later in the equation. So here the error signal, which is nothing but the partial derivative of the gradient of the loss function with respect to the Z1 for neuron 1. So this we cannot calculate directly, so we're gonna represent this in chain rule with two components, multiplication of the two gradients. So this one, gradient of loss function with respect to A1, we calculated this in previous step during the activation, multiplied by gradient of the A1 with respect to Z1. So this you can see it's the derivative of ReLU itself. So ReLU derivative we calculate 0, so this will come here and this would be 0 and this whole term would be 0 here. Let me clear this up a bit. So we calculated the error signal for neuron H1. Now similarly we're going to calculate this for H2. So here we have the same thing. Instead of A1 we will have A2 and Z1 we will have Z2. The ReLU we have Z2. So this value we already calculated before, and this Z2 is phi we calculated during the forward pass. So if it's positive, if the derivative ReLU of Z, derivative ReLU of phi is 1. So that's why we'll have 1 here and we'll have the same thing here in the output. So notice that the ReLU, where the ReLU is off here in this part for the H1, because it's 0, the gradients won't be passed back. So now let's calculate the gradients of first layer parameters, which is the step 7. So here we are. So we're gonna move from this weighted sum and we're gonna calculate the gradients with respect to the loss function, the gradients of loss function with respect to each of these weights. these four weights and these biases. So let's see for the hidden layer neuron 1. This is the weighted sum function. So again, here we're going to take the partial derivative of this with respect to each of the weights and bias, which is the parameters. So if we just do partial derivative, we'll get these results with the corresponding, which we already did before. As usual, now we're going to apply chain rule. We're going to do it 2 times because we have 2 hidden layer neurons. So this is for neuron 1. So neuron 1, the incoming weight is these two, W11 and W12. That's what is given here. So we need to calculate this, and the bias associated with one, which is this one. So this one can be written as this formula, which is the error signal in hidden layer neuron 1 multiplied by the input, which is given here. How? Because this with chain rule can be expanded in this form. So here in the denominator we have Z1, which is the weighted sum output. So this value we calculated previously before in the previous step, the gradient, and this value we are calculating now, which is calculated from this step. So here we can receive this from here, which is the x1 itself. X1 is the input, so we'll have 1, this one here, and this one from previous step we saw the gradients are 0 because the ReLU it's turned off there. So we'll have 0 in every term, so we'll get 0 everywhere. So similarly for we're gonna do the same thing for the hidden layer neuron 2 H2. So instead of this Z1 we will have Z2, and what are the incoming weights to Z2, which is 2-1 and 2-2. So we'll have 2-1 and input 1 and 2-2 from input 2, and the bias step it will be B2 instead of B1. So similarly we'll have partial derivatives of this. So at the end for neuron 2 we will have we're gonna find these 3 partial derivatives, these 3 gradients, which is the weights and the bias associated with second neuron of the hidden layer, which is the similar case. And here the error signal is not 0. If you remember, error signal is we calculated before, which is this term gradient with respect to Z2. Here it's Z1, for this one it's Z2. So this we're going to substitute that, and X is the input, which is 1 and 2. So we'll get those, and even for bias you will get the same term. So now if you recall, we calculated the gradients of all the weights and the bias, which is all the parameters we calculate for this and these biases and all the weights. So let's see how we can use them to update the weights. Now let's see what happens during the forward pass with updated parameters. So let's start again from the input and see what we get as the output with the updated parameters. But take a note that H1 we don't need to calculate because it doesn't have any effect. So we need to calculate first the Z2, which is the weighted sum of hidden neuron 2 incoming weights, and we need to multiply it with the input. I just denote everything with a dash to mention that it's with the updated parameters. So for H2 we have W21 multiplied by X1, which is W21 we have here. We just do it here, and this one is the input, and similarly we have W22 multiplied by X2. X2 is 2, and W22, the updated one, is this one. Similarly, plus the bias is the updated bias, which is we get it from here. So we do that and calculate the weighted sum, and for the activation it's just the positive value. So for ReLU is just the same value itself. Similarly, we calculate it for the output, the weighted sum of the output, but instead of the input we will have this value here, and similarly we will have the predicted value y cap, so which is the sigmoid of this z out, and we'll have this value. So here we're going to calculate the loss because the class is 1, the loss function BCE binary cross entropy, the formula is minus log of y cap, so it's the loss we will get as 2.2310 if we calculate it. So if you clearly see, before doing anything the original loss was 5.006. It has clearly reduced to 2.2310 in a single step, in a single epoch. So in real time, multiple epochs could be done to reduce the loss from a big value to a smaller value. So this is how a neural network updates the weight and updates the parameter in order to reduce the loss. So for the final part of the video, let's see the other scenario. So the neural network which we consider is for binary classification. So here we use, in the output part, we use sigmoid as the activation function to squash the values between 0 and 1. And we use the loss function as binary cross entropy loss too. So what happens if there are other cases, like instead of a single class being 0 or 1, if there are multi-class classification with single label, like we have a digit prediction from image of handwritten digits, we have 0 to 9 digits, so we have 10 class in total. So what in that case, instead of one output neuron, we have the k neuron, where k is the number of output classes. We have that many neurons, and we used another activation function called softmax, which is used to give the probability distributions, which is useful for calculating the loss function gradient. And in the loss function, instead of binary cross entropy, we have categorical cross entropy, because the probability needs to be like considered across all the classes, so it need to be normalized across all classes. So we use the loss function. And similarly for regression, we don't have any activation, so we just use the linear activation. And for loss function, we can use mean squared error or mean absolute error. So this is kind of explained in the logistic regression video. So no matter the activation function or the loss function which we use here, the neural network algorithm or the mechanism remains same. So both in the forward pass and in the back propagation, everything remains same. So the changes only happen in this part or here, where the activation functions might change according to different needs and as the user assigns. So but the logic is same. We're gonna back propagate the loss to every layer, and we're gonna update the weights. So there is another form which we can represent, and we can do the calculation, which I said, which is done by the Python libraries now, which is the matrix form. I didn't explain it because although back propagation here and the forward propagation, if it is written in matrix form using a thing called Jacobians, which we might discuss later in later videos. So this is only a compact representation. So conceptually, learning happens neuron by neuron via chain rule. So the matrix form just groups identical operations together so that it would be easy.